Today I'll be discussing the solution for leaf fall and discuss how linearity of expectation indicator variables help uh, destroy a problem that's suspected to be 2700 rated. But if you know these concepts, it boils down to just implementing it quickly. So let's look at the problem statement once. I'll have the link of this from the description. So you're given a tree with n vertices, and over time, each vertex I has the probability of pi by qi of falling. Determine the expected value of the number of unordered pairs of distinct vertices that become leaves in the resulting forest. Modulo sum, modulo this famous prime. Note that when the vertex v falls, it is removed along with all the edges connected to it. However, adjacent vertices remain unaffected by the fall of V. And some important definitions here is that a leaf is a vertex that is connected to exactly one edge, which will be important later. And forest is just a graph of the cycles, which means it's a bunch of trees. And an unordered pair is a collection of two elements where basically if you have 1 2 1 2 then 3 5 and 2 1 and 5 3, they both are considered the same set of pairs. Now the constraints are normal, so there's no trick there. And let's dive into an example. So the samples are pretty nice, but I initially had a doubt whether only one vertex can fall or any number of vertices can fall, which I later asked and was clarified. So in this sample case, you have a line graph of length 3, and so the different cases are 1 falls off, and so 2 and 3 are leaves. So here there are 2 leaves, so 1 unordered pair. 3 falls off, so there are 2 leaves, that's 1 unordered pair, and none of them fall off, so there are still there's 1 unordered pair of leaves. And so probability, and so if you use the normal formula of expectation, which is sum of occurrences and the probability of that occurrences, you get the answer 3 by 8. So let's take a deep dive into understanding this problem. So first, if you look at the definition of a leaf, so let's say you have a current vertex V, which is connected to some number of vertices, right? Now it becomes a leaf if all except one edge gets deleted, and an edge gets deleted only if the vertex gets deleted. So if there are 4 vertices connected to it, so you have 1 2 3 4, and you have your main vertex, that's 5. So in this set of 5 vertices, for V to be a leaf, there are 5 events that need to happen. One is this dying, and this dying. So when I say dying, I mean falling off. I'll be using them interchangeably. Dying, this dying. You will want this to survive, and this to survive. So the probability of the event that V becomes a leaf is conditioned on these 5 events happening together. And since each vertex dying is independent to another vertex, so you could just multiply them. By that, what that means I'll clarify later. So starting off it, let's make use of indicator variables. So this is just a fancy word for a variable I that's associated to the vertex. So associated to the vertex I, which it becomes 1 if I is a leaf and 0 otherwise. So if I is a non-leaf node or has fallen off, in both cases the variable will be 0, otherwise it will be 1. Now what we are asked to calculate is number of unordered pairs. So summation of I summation of j greater than I to make sure we count the pair exactly once. Ij. So, but we do it for all nodes since ii and ij will only be 1. So this will only be 1 if ii and ij both are 1, and that means both of them are leaves. So in turn we are just calculating the number of unordered pairs, which is what the problem was asking. So now so for given state we could use this formula to find the number of leaves, the number of pairs of leaf. But now in order to find the expected value of this, let's use another concept called linearity of expectation. So this basically tells you that if the function expectation, if applied over a set of linear combination of random variables such as this, then you could simplify it to write it as expectation of x plus b times expectation of y. So I use the term random variable here, but so just to give a brief idea what a random variable is. So random variable is just a function which goes from the set of events. So you have any set of events. So it could be a coin reaching heads or coin reaching heads thrice, or in this case a vertex being a leaf. So set of events, which is in our case the vertex being a leaf, to some number in the real space of numbers, right? So in this case our random variable is ii, which maps from an event of the vertex being a leaf or not to 0 or 1. So we satisfy the definition, so linearity of expectation would work on our indicator variables too. So simplifying now, expectation of summation I equals 1 to n j greater than I to n ii ij is equals summation I equals to 1n summation j greater than 1n expectation of ii ij. Now as you see, now we just need to worry about what any two vertices, so what the expected value of this is, right? Now but there's another theorem that says that if two random variables x and y are independent, then you could write expectation of xy to be expectation of x times expectation of y. Now the idea of independence is that so if two events are independent, let's say x and y are independent, then that means that no matter if y becomes, to give another example, let's say I have two coins. So I have coin 1 and coin 2. So let's say there's a random variable x1 that's dependent on the outcome of c1. So if c1 is heads, then x1 is 1. So x1 is basically c1 is equals to heads, and c2 is and you have another random variable y that says c2 is tails. Now you understand that x being equal to 1 or 0 is completely doesn't depend on y on c2 being heads or tails, right? So then automatically x and y are independent and you can use this. Similarly, in our setup, if you have a vertex here and you have some vertex quite far away, now the probability that after series of events this becomes a leaf and probability that this becomes a leaf would only depend on the vertex neighboring it and the vertex neighboring it. And as you see, if these set of vertices have no intersection, that means there are no vertices that any of these. So let's say, let me name them. You have vertex A and vertex B. So if the event of A or B becoming a leaf isn't dependent on a vertex X, such that X belongs in both of their dependent sets, then A and B's events of A and B becoming leaves are independent. So we'll get the exact condition soon, but for now, actually I can get into it right now. So as you saw that the probability that V becomes a leaf is just dependent on the vertex itself and its surrounding neighbors. So if I denote a variable n of V, denoting all the neighbors of V, so formally all so it's a wall vertex X such that distance of X to V is equal to 1. So notice I'm not including V itself, but just only the neighbors. So if for two vertices A and B, if neighborhood of A and neighborhood of B do not have any intersection, then they're independent, because NA denotes all the vertices that it depends on and NB denotes all the vertices that it depends on, right? And since they don't have an intersection, then we can say that they are independent. So one case is, so what's the smallest, so if you want to formalize this, what would we do? So if there are two vertices that don't share any neighborhood, think about why it's equivalent to say that if neighborhood of A intersection neighborhood of B is equal to 5, then the distance of A comma B is greater than 2. So it's easy to see that you have an A, if they're equal to 2, so let's say they're joined by vertex, then X, A being a leaf or not is dependent on X's events, and B being a leaf or not is dependent on X's events again, so they're not entirely independent. And if distance is equals to 1, again obviously they're dependent on each other's falling or not falling, or to determine whether they're leaves or not. And obviously if they're same vertex, then we're not bothering about that. So now we know that if distance of AB equals to 2, we can they're independent, and so we can use this formula. Now coming back to our summation, so if I and J have the following relation, that distance of I and J is greater than 2, then expectation of II, Ij is equals to expectation of I times expectation of J. Now let's consider the case when their distance is before we go further, let's tackle what is this term expectation of II. So expectation basically is, so if, let's say if an random variable x, so if I want to find the expectation of x, I basically sum over all variables, all values that x can take. So let's say for simplicity, let's deal with x going over a discrete space. So or v being the range of x. So for all values that x can take, it's the summation of the value and the probability that x is equal to the value. Now, in case of an indicator variable II, it can take 1 or 0. And since 0 times anything does is just 0, we can only be bothered about the probability that it becomes a leaf. Now how do we formalize this? So we know that for it to be a leaf, one, so let's look at a vertex A. One is that A shouldn't die. Exactly one neighbor of A should live. So these are necessary conditions, and with some work it's obvious that it's also sufficient trivially. So how do we formalize this? So what are we given? We're given the probabilities that it dies. So we are given di, which is equals to pi by qi, which is probability I dies. Now let's say we have defined n of a to be the neighborhood, that's all the vertices with distance 1. Now to formalize what I've written here, we need to, one event is A shouldn't die, so this has a probability of 1 minus dA, and let's say L belongs to some vertex L in the neighborhood of A lives, so this has a probability 1 minus dl of happening, and for all vertices K belonging to the neighborhood of A such that K is not equal to L, we have it dying, so that has a probability of dk. And since any individual vertices dying or not dying is independent of each other, the probability that all of them happen together will be multiplied. So the probability of IA equals 1 is equals to summation for all L belonging to the neighborhood of A. You have 1 minus dl being the probability of it living, here 1 minus dA, and then you have the product over, so the big pi is a product over all K such in the neighborhood such that K is not equal to L and its probability of dying. Now computationally, since we are going to write a code for it, a simplification could be to rather than remove this subtraction and multiply by dl and divide by dl, so we have a term which is more generally usable. So this becomes summation L belonging to neighborhood of A, 1 minus dl, 1 minus dA, and you have pi of K belonging to NA with no restrictions dk. And sorry, I have a dl term here, and these terms are independent of what L is chosen, so we can remove this out. So that is 1 minus dA times pi of dk, K belonging to neighborhood of A, times summation L belonging to neighborhood of A, 1 minus dl by dl. So we now have few terms which seem to be elegant enough to pre-compute and store, and I would be spoiling that they will be useful later. So let's call prod A to be pi, so the second term here, since I'll be using them soon, and since it's a probability of it living or dying, let's say LD A to B summation L in neighborhood of A 1 minus DL by DL. So you have this term and you have DA. So you right now, if you think about the implementation, you have three vectors: your DA, which would be formed by dividing P and Q, the prod, which is the multiplication of all the dying probabilities of the neighborhood, and LDA, which is the summation of the ratio of probability of living to dying over its neighborhood. Now, so we can rewrite the probability of it being a leaf to be 1 minus DA times prod A times LDA. Now we have this, and this is also equals to probability of IA equals 1. So now to find the expected, now it should be obvious that the expected value of IA is equals to 1 times the probability IA equals 1, which is P leaf. So now we can get back to our original problem of considering the pairs of vertices when they have a distance greater than 2. So this is equals to P leaf I times P leaf J. So now we have sorted the case when you have distance greater than 2. But what about when the distance is, let me see if I was in frame. Yeah, I'm still in frame. Sorry, I just had to check. So we've dealt the case when they have a distance greater than 2. Now for the distance equal to 2. So when IJ have a distance equal to 2, you have vertex I, you have some vertex K that they both neighbor. Since it's a tree, there'll be exactly one vertex. And let me just drink some water. So you have some vertices that it's neighboring, some vertices that it's neighboring. Now remember the conditions for now we are trying to find expectation of II times IJ. Now I can't separate them here because they are not independent. So, but again, since each of them can be either 1 or 0, the probability of both of them, the product of them being 1 is same as the probability that both of them are 1. So this equals to just probability II equals to 1 and IJ equals to 1, right? Now so if you remember, the condition for it to be a leaf is that this should live, and now since these are independent events, let's just write that down. And at least exactly one of its neighbors should live. So now there are two choices. Either K is a neighbor, so let's consider when K lives. So since K is living, every other neighbor should die. So for all V belonging to the neighborhood of I and J, and V is not equal to K, we have dV. So this is the probability of both of them being a leaf, assuming K lives. Now what if K dies? Now if K dies, yeah, one of its neighbors from here would live. So that would be 1 minus DI times 1 minus DJ times dk, since we know it's dying, and now we would have some neighbor of it living. So how do we tackle this scenario? Probability exactly one neighbor lives. So if you observe this scenario from a single leaf's perspective, we know that k is dying. So if you look back at the formula which we derived for a probability uh, of leaf being alive, so you have this term which would this signified of a living, and you have this term which signified of all its neighbors dying, and this term of exactly one neighbor living. Now since we know that k is going to die, we can remove this term. So you can remove k term from here, and we can keep k here. So we can rewrite this as we would have 1 minus di times 1 minus dj times dk times, so probably that all its neighborhood dies, which I named it as prod. So prod I, but since we already have a dk here, we don't need to add it here, times all its neighbors die. We don't need to add it again. And times, so now we have to multiply with the probability that exactly one of them live, but we know dk won't live. And so I think I named that variable as ld, yeah, sorry. So times ldi minus these terms times ldj minus 1 minus dk by dk. So this lengthy shit is our formula for what happens when k dies. So if we group like terms together, which is an important practice to do, which since it would simplify implementation, as you will see later. So when k dies, it's 1 minus di times so I can just cancel one term here. So 1 minus di prod I ldi minus 1 minus dk by dk, so times 1 minus dj times prod j times ldj minus 1 minus dk by dk. Now we have the divided by dk term, since we'll be over counting it. So this is the probability if k dies. So looking at all of this, you would think that implementation would be stressful, but as you would see later, a single function would take care of many of these sum of products. So, and we can simplify this probability further, since we can remove this abstraction of not including k and just multiply the products and then remove k's term, since it's the only thing that's common. So you have prod I, prod j divided by dk square. So you have, so now we finish with the case when di equals 2. Now since this was the most complicated case, now we'll just move on to probability when the distance is 1. Now case 3, distance of I j equals 1. So in this case, since both are leaves, we know both are alive, since you can't be a leaf when you're dead, since those dead vertices don't participate in the final arrangement, and we only count leaves in the final arrangement. So since both of these are alive, we know that in our formula for leaves, so if to look back at it, so in our formula for leaves, we know that we know exactly one of these terms is going to be there, and so in that case we can just write down the probabilities as, so let's say this is vertex I, this is vertex j. The probability of that happening is 1 minus di, that probability of this living, times 1 minus dj, probability of this living, and times, so all the neighborhood are dying, so that is prod I, but we know dj is living, so we'll remove it, times probability that all its neighbors dying, prod j, times probability that di dies. Now we can so this just remains to be the term. So now we have 3 probabilities which we've derived, which I'll just write down separately. So you have one case when their distance is equal to 2, one case when the distance is equal to 1, and another case where they have distance greater than 2. So let me just highlight that. Yeah. So you have case 1, case 2, and case 3, right? So now let's boil down to implementation. So in implementation, we know that we will need a few vectors. So one being d, the dying probability, prod, the product of the dying, and 3 being LD, which is probability of the ratio of living to dying, the sum of the ratio of living to dying over all the neighbors, and 4 is probability of the leaf, and yeah, that's it. So now for case 3, when distance ij equals to 1, you can iterate over the edges easily by no of m, which is O of n, and add this up. But in this case, when distance greater than 2, the worst case scenario could be of m square, since you would have to iterate over all your neighbors. Assuming you iterate as k, you would have to iterate over all your neighbors and all the pairs of your neighbors, which can be of n square, for example in a star graph. So if you do it naively, it could take so long. Instead, what you could do is, since you know if you fix a k, so in case 2, when you have I, k, j, if you fix a k and you know that the total probability for all your neighbors, the total expectation, sum of expectation of ii and ij for all your neighbors I and j is sum of k lives and sum of k dies. And since these two sums can be represented as so they're of the form summation ij fi fj. So you can use this neat trick since this is just equals to summation fi whole square minus summation f of I square divided by 2. So you can work it out by hand and see why this is true, but we'll use this neat trick to find the sum of these products in O of m. So now to write down the terms more neatly, so in k lists you have this, so I'll just see this times prod I, this times prod j, and you have this extra term which is multiplied to every term, so you can do that later by d square. Now in k dice, so let's say this is function fi and this is fj, and k dice, allow to name it better, li, lj, and k dice is already separated nicely here. So you have this term which, let's say, kdi, kdj, and we know we can apply this formula to it. Now for the cases when where is it? So when the distance of ij is greater than 2, you have it here, right? So this is again, so when you have to iterate over all vertices who are distance greater than 2, naively it's obviously a quadratic, which is too slow. So since this is again a sum of products of two same function, you can again reuse this particular trick to get the sum of products. So we can so now in order to add all these cases up, we know that the number of pairs of products such that it's greater than 2 is much more than any of equal to 2 or 1 or usually. So in that case, what we can do is we can start off with calculating this summation, but not just for vertices greater than with distance greater than 2, but for all vertices. And then for each of these cases, when distance equals to 2 and distance equal to 1, we will subtract its wrong sum contribution and add its correct contribution. If you're confused on what I mean, we'll go down to implementation and maybe that'll clear you up. So I'll be using Touris's Mint template for this. So you have your mint, you have your, so you take your input, so you have your number of vertices, you have the probabilities. So since I'll be using vectors of mint a lot, just make alias, and you have vmpq, and you have a vector of edges which you take as input. And yeah, that's it. So you take P, then you take Q, Now for all vertices, yeah, pi qi. So you have n minus 1 edges for all vertices in these edges. For all edges, you take input and return back to 0 BSC indexing. That's my preference, but you can choose not to. So first we'll make our vectors. You have D, you have is leaf, your probability of being a leaf, and you have LD, which is the sum of ratios, and you have what was the prod? Are there any other? Cool. So it's all these. So now for all vertices, I would write di is equals pi by qi, and now the first let's calculate probability of it being a leaf or of prod, since that just relies on D. So for int I is equal to 0 less than n I plus plus. Now for all the neighbors in I, you could initialize prod to be 1 and prod of I multiplied by probability of it dying. Then calculate sum of the ratio of living and dying. You have LD of I equals 0 for auto j and adjacent of I. LDI plus equals 1 minus di by di. Now we'll calculate leaf. So leaf of I is equals to, so 1 we know is that it needs to live, and we know that all its neighbors, so most of the neighbors should die except 1, so times prod I times LDI, which has the correction term. Next we have our answer. Now since the function getting the sum of products from a vector of fi is going to be used twice, it's better to make a lambda. So auto sum prod, which would take a vector as input, and so one would take the find the total and one would find the sum of squares. Now for each variable in the vector, I add the total and I add the sum square, and then sum square and divide by 2. So now we'll start off with our answer without caring about the case 2 and case 3. So answer is equals to sum prod of it being leaf. Now for cases, first we'll handle the easiest case, which is when they have a distance equal to 1. And so we'll remove the wrongly calculated term, which is probability of leaf into leaf x times leaf y. And we would add the actual probability which we calculated to be here. Probability x lives, probability y lives, times prod I times prod j divided by di times dj. Sorry, I used ij. Yeah, so we have accounted for distance equals to 1. Now for distance equals to 2, we iterate over the k. Now we'll first have the correction term. So first let's store it in here. So first we would make a vector with the correction terms to add the sum of products to later. Then we would have a vector for case k live and k dead. So this is kd, and L. So you have vector L and you have kd. Now for each neighbor, the correction term is the probability it becomes a leaf, and the L term, the probability of it when k lives, is prod I times I minus di. Minus di. And kd term is 1 minus di times prod I and ldi. Okay, so we have kd. Now first we get the correction done. Then we add the alive part, but we haven't accounted for 1 minus dk by dk square, so we'll multiply that at the end. Square. And the dead part, is there any other term missing? By dk. Okay, so that's done, and then we add the contributions to our answer. At the end we print it. Oh, I didn't make the adjacency list. I think this is the first time that's happened. Now let's test. I think that's very wrong. I wonder why. Let me see if they can improve properly. Is my mod correct? It's mod 2. Alright, I did do that. Oh yeah, I didn't do sum of products, so I have to square total and subtract it. Is this right? Nope, it's still wrong. I wonder why. Okay, so this is correct. Let me just make sure adjacent list is correct. Product of all its neighbors dying, so I multiply that product, DJ. Now LD is the sum of ratio of it living and dying. Oh, here's a bug. And there's supposed to be another bug, I think. Yeah, there's some other bug. So probability of distance one case was let me just 1 minus dx times di times product of x living, product of all of its neighbors dying, divided by x and y actually dying. So this seems to be correct. And here the correction term is also correct, I think. Yeah. For living probability is prob by prod I times that, and then for some products I divide k square and multiply with my probability of me living, and probability of the neighbor living, all its neighbors dying, and so we remove the probability that k lives, and we remove 1 dk for that, since they are common answers, and we divide by that. Okay, I'm not sure where the bug is, but let me just debug and see if everything's in order. Now for this case, so in case 2, all of them had a probability 1 by 2, 1 by 2, so it should be easier to analyze. So they all will have the same probability of dying. They should have a 1 by 8 probability of it being a leaf. LD for some reason is 1 to 1. And if that's anyway close. confirm if the model answers are correct. Power to and 1 by 4 is 7 4. Cool. So you have 1 by 1 by 2 1 by 2 1 by 2 1 by 2 1 by 4 1 by 4, and LD is, so each ratio would be just 1, so that's just number of neighbors, 1 to 1, so this is correct. Probability of being a leaf is going to be LD times probability of it living and all its neighbors dying, so it's 1 by 4 in this case, and 2 times 1 by 1 by 2 times 1 by 4 is second 1 by 4, so all this is correct. So all this is correct. Then where's the mistake? So I remove here and I get this 1 minus dx times 1 minus dy times products times prod y by dx times di, and the correction terms this is correct, right? So I add the terms, sum of square it, subtract the sum of squares, and divide by 2. Yep, that's correct. So 1 minus di 1 minus di prod j. Oh, I'm really dumbstruck. Oh. Sorry about that. So that's a stupid bug. Four 8634106 so you can try submitting it. Code forces. Sorry, this is in practice. Yeah, it should pass. Yep, so that works. So this was the tutorial, apart from the stupid bug which we uncovered in the last moment. But yeah, Thanks for watching, and if you have any doubts, leave it in the